Hello and welcome. My name is Dominik Schröder, and in this video we are going to talk about pseudorandom functions, so stay tuned. Before we are ready to understand pseudorandom functions, we're going to take a look at the definition of functions, of non-random functions, and of random functions. So let's get started. So to describe a function, you can actually define it by looking at its input and output behavior. So here we will start for simplicity with a function that takes as input strings of length n and will produce strings of length n as well. You can come up with a more general definition where you map n-bit strings to n-bit output values. So if you want to describe this function formally, one way that you could do is essentially by writing down the whole input and output behavior. Assuming that we have strings of length n means that we have as input 2 to the n different values, and each of these 2 to the n different values will produce one output value, which means for each of this value we will have one output value. So in order to store this function fully, you will need n times 2 to the n. So do we need the space in general? And the answer is no, because there are functions that actually have a lot of structure and where you can come up with a very short description. The first of these functions is, for example, the constant function, which is obviously not random at all. So consider, for example, the constant function that maps all of the values to the output value of 5. Clearly this function is not random and has a very short description. And this brings us to the definition of a random function. So a random function behaves exactly the opposite, which means there's no way to compress the description of the function. In other words, when you query the function on some value, it does not leak any information about the function's behavior on any other value. And therefore, to describe this function, you indeed need n times 2 to the n bits. Why? Because each of the 2 to the n input bits has exactly one output that corresponds to a string of length n. And therefore, the overall space to store this function is exactly n times 2 to the n. So now we have seen the two extreme cases. First of all, the constant function with a very compact description, and on the other hand, a random function where you actually need exponential space in order to store this function. So what is a pseudorandom function now? Well, a pseudorandom function somehow is in the middle in the sense that you want to have a somewhat compact description, and at the same time it should actually behave as a random function. In general, a fixed function can never be pseudorandom, and therefore we need to generalize our definition slightly and take a look at so-called keyed functions. So a keyed function essentially takes as input two values. One is the key, as the name suggests, and this is chosen uniformly at random at the very beginning and then fixed during the entire execution of this object. And the second value is the actual input value. Now, as you can see here, the function takes as input two arguments and produces an output value. So now what does it mean for a keyed function to be pseudorandom? Intuitively, what we would like to achieve is that the function somehow looks as a random function. And usually in cryptography, whenever we have such somehow looks like definitions, we think about indistinguishability notions, which means we are thinking about a mental experiment in which then an algorithm has to decide whether it's interacting with a pseudorandom function or with a random function. And this is exactly the game, as you can see here. Here in the middle we have the distinguisher, and he's actually living in one of these two worlds. So either talking to the pseudorandom function or talking to the random function. And in one of these cases, it doesn't really matter in which one, the adversary outputs 1. And now the intuition is essentially, and also our formalization, that the adversary roughly outputs as often, let's say, the value 1 in the case that it's interacting with a pseudorandom function, as well as it's interacting with a random function. In other words, the distinguisher cannot really tell in which world it is actually living. So let's take a look at the formal definition now. So we are now turning this intuition into a formal definition. And this definition looks actually as follows. So first of all, we're defining the function. And we're doing this in the following, that we say, let f be an efficient length-preserving keyed function. So length-preserving actually means that the size of the key as well as the input and the output are all of the same length. And this is just for simplicity. You can, as I said before, come up with a more general definition where these parameters are different. And now we are saying that f is a pseudorandom function if for all efficient distinguishers the following equation is actually negligible. So let's take a closer look at this equation. So we are taking a look on the left part, and here you can see that the distinguisher gets black box access to the pseudorandom function. As I said before, the distinguisher doesn't know in this case that it's interacting with a pseudorandom function. And here we're computing the probability that the distinguisher actually outputs 1. And now we're taking a look at the right side, and the right side essentially says roughly the same, but now the distinguisher gets access to a random function. And we are actually requiring that the difference between both probabilities is negligible. So now let's take a quick look on how these probabilities are actually computed. Well, in the first case, the probability is computed over the random choice of k, meaning over the random key that we have chosen. In the second case, the probability is taken over the random choice f of the set func n. And by func n, we actually mean the set of functions that have the corresponding input and output behavior. So this concludes the description of the definition. So how can we construct pseudorandom functions? Theoretically, this is one of the major open questions. In particular, one can show that the existence of one-way functions implies the existence of pseudorandom functions. And as you probably know, we have no idea whether one-way functions exist or not. And answering this question would also solve the question whether p does not equal np. So making progress here is quite hard. So what about constructing pseudorandom functions in practice? Well, here we know that, for example, we can use hmac as an instantiation as a pseudorandom function, or there are also constructions based on symmetric ciphers such as AES to instantiate a pseudorandom function. Pseudorandom functions are often used in cryptography. We not only use them to de-randomize algorithms, we also use them, for example, as message authentication codes. And we're going to take a closer look at this in upcoming lectures.